Okay, can you see the screen?
Yes, we can see it.
Yeah,
Thank you very
perfect.
much. So now we have Jürgen from University of Malta, and he's going to talk about cosmological signature of a modified dark sector. So thank you very much, Jürgen, for accepting this invitation.
Okay, so thank you for organizing this workshop, and thanks for the invitation. Yeah, so as Julie mentioned, so I will be discussing the cosmological signatures of modified dark sector. I will start off with a brief introduction of the general Einstein equivalence principle, and then how this is related with the equivalence principle within the dark sector. Okay, so we have heard about modified gravity in previous talks by different speakers. And in this case, I will not be dealing directly with the direct modification of gravity itself, that is the geometric part. However, I will be dealing mostly with the energy momentum sector modification itself, which obviously feeds back into the geometric part as well. So as I said, I will start off with the violation of Einstein's equivalence principle and considering some phenomenological parameterizations, as well as the current constraints that we have from existing data at the moment. And then I will move on to the main theme of this talk, which is basically the violation of the dark equivalence principle. Um, um, and then in which I will introduce a theoretical framework, which is a generic framework, and then we will deal with a number of cosmological signatures at the background level as well as at the perturbative level by considering the growth history as well as the integrated Sachs-Wolf effect, and then I will end with the current parameter constraints on these problems. Okay, so first of all, yeah, just as a brief introduction to GR itself, we know that Einstein's equivalence principle is one of the main building blocks, okay, of GR, and this is the principle which allows us to identify the effect of gravitation with Eckert space-time geometry. So in general, we have already came across this in previous talks. We consider the matter sector. Okay, so we consider the matter sector denoted by here the action formalism as matter. That is basically composed of the matter Lagrangian, okay, with which is explicitly dependent on the metric G mu nu, as well as the matter fields, which I denote over here with psi. Okay. Now, in the case of metric theories of gravity, first of all, when we consider these kind of theories, they fully embody the Einstein's equivalence principle. In which case we have that space-time is described by symmetric metric. Okay, if you consider trajectories of freely falling test bodies, you will end up with what are known as geodesics of that metric. Okay, and in the case of local freely falling reference frames, the non-gravitational laws of physics are those written in the language of special relativity. Okay, so we all know these basic elements, okay, of metric theories of gravity, and we know that the Einstein equivalence principle is verified with a very high accuracy within the solar system with a number of tests. Okay. So now, what happens if, first of all, I'd like to have a look at how I can break this equivalence. So first of all, the gravitational interaction within the GR framework, we know that this is mediated through one metric tensor, right? So that is the G mu nu tensor, which I have already introduced. However, we know, and even with reference to the previous talks, that there are a number of extensions to GR. And most of the time, we end up with additional fields. Okay, so most of the time we end up with scalar fields, for instance, but you can also end up with vector fields and tensor fields. But in the generic case, when we consider an extension of GR, we will end up with an additional field, whatever that field is, right? And in this case, what can happen is that these fields can have a non-minimal multiplicative coupling to the matter fields. So if you remember from my first two slides, when we considered the matter sector, all right, there was an explicit coupling between the metric tensor, right, G mu nu, and the Lagrangian of that matter sector. So if you have a field and you assume that there is, or as there can be, a non-minimal multiplicative coupling, then at the Lagrangian level, you will end up with this coupling function, which over here I am denoting by h of phi, which will basically appear at the Lagrangian level as a multiplying factor with the matter Lagrangian. And in this case, for simplicity, I will just be considering the electromagnetic sector as my matter sector. So if I consider a scalar field phi, all right, with a coupling h of phi, which is only acting in the electromagnetic sector, then that will explicitly appear at the Lagrangian level. So what are then the observational effects of such a coupling? So if we consider the reciprocity relation, okay, we know that if we consider the standard theory of gravity, this relation holds, right? And also we know that the number of photons is conserved. And via these two facts, we know that we have the distance duality relation, right? Which is a cornerstone as well of gravity theories. So basically, we end up with a relationship between the luminosity distance, dl, and the angular diameter distance, dA, right? Where basically, if I multiply dA by 1 plus z squared, I end up with the luminosity distance. So in general, I can parameterize any deviation, okay, between the luminosity distance and the angular diameter distance by simply considering a parameter eta of z, okay, which will just be the ratio of these two quantities. And definitely, in the case of standard gravitational theories, eta of z is exactly equal to 1. Once there is a slight deviation, okay, so from standard gravity, then I will be expecting eta to deviate from 1. So what are the consequences then of the non-minimal multiplicative coupling? So if we look at Maxwell's equations, okay, we'll end up with these modified Maxwell's equations in which you don't get the standard equations, in which now I have h of phi, which is being multiplied by the Faraday tensor, okay? And as a consequence of that, when we consider the geometric optics approximation, we'll end up with the first two equations, okay, for which we have the wave vector, k mu in this case, which is appearing in these two equations. Those are the standard equations, okay? So with the first two equations, we know that photons are still propagating on null geodesics, okay? So like in the standard gravitational scenario. And therefore, we know that then the reciprocity relation still holds. However, when we look at the last equation, okay, so again, this follows from Maxwell's equations, we end up with a deviation, okay, so from the standard equation. So as you can see, the right-hand side over here is non-zero, okay, it's dependent on the coupling, h of phi, and this, therefore, implies that the number of photons is no longer conserved, i.e., we get a violation of Etherington's relation, right? So there is now a violation. So when we consider a flat FLRW metric, what will happen is that I will modify the luminosity distance, okay? So in which case I will get a prefactor, okay? That is, in the luminosity distance, I will get a term dependent on the coupling, okay? So which is dependent on the square root of h of phi evaluated today divided by h of phi, okay? So at that particular redshift z. However, since the angular diameter distance is a geometric feature of the metric, that is basically unchanged. However, when I then consider the phenomenological parameterization eta of z, and I take the ratio of these two, I will end up with an eta of z which is not identically equal to unity. Okay, so it's basically proportional to the ratio of the evolution of h of phi. So then there is a direct link of this multiplicative coupling with one of the fundamental constants of nature, which in this case is the electromagnetic coupling, okay, i.e. the fine structure constant. And via a three-level analysis, you will end up with alpha, okay, being the electromagnetic coupling or the fine structure constant. You'll end up with alpha being proportional to the inverse of this multiplicative coupling in the electromagnetic sector. And from this relationship, we will end up with a variation, okay, a temporal variation of the fine structure constant, which I can write down explicitly in terms of the multiplicative coupling h of phi, or in terms of the violation of the phenomenological parameterization eta of z, okay? And if we consider a number of phenomenological parameterizations, okay, like for instance, a linear eta of z, okay, with eta 1 being our new parameter, you will see that current data sets are consistent with a null deviation, okay, at the level of 10 to the minus 6, okay? And by even considering a different parameterization, so now considering the relationship of z divided by 1 plus z, again, we will end up with very similar constraints. And even in the case of logarithmic kind of evolution for eta of z, we still get to the null variation of the fine structure constant, or else that is a very good agreement with the reciprocity relation. Okay, so over here, I just wanted to introduce, let's say, when we consider a coupling within the normal matter sectors. Okay, so that is within, in this case, the electromagnetic sector. We know that there are very tight constraints. Okay, so that is just one example. Now, what happens if I just consider the violation of the equivalence principle within the dark sector only? Okay, so we know that the dark sector is composed of the dark matter as well as dark energy. Okay, which in our case, we will be considering dark energy being represented by a scalar field, which will be coupled to dark matter. So first of all, if we consider a phenomenological interaction, okay, so let's start off at this level, and we consider the dark sector to be interacting, okay, we can therefore consider lambda, okay, so the standard lambda, as a running parameter in curved space-time version of quantum field theory. So basically, if I consider lambda as a function of redshift, in this case, it's a function of h, okay, what will happen is that when I consider the Bianchi identities, I will end up with an energy transfer between cold dark matter and the energy density of lambda of h, the decaying or dynamical lambda in this case. And the current indications, so with the current data set, are that, for instance, if I just consider lambda of h being proportional to, so we've got the lambda term, so the constant term a, plus an additional term bh squared, and turning off the c term in this case, so for this contour plot, what I'll end up with is that basically current constraints are very well consistent with a zero, with a zero deviation from a constant. Okay, so that is from the standard lambda dm scenario. Okay, however, you can get a slight preference to a non-zero dynamical lambda when you consider, let's say, the large-scale structure data with the CMB data. Obviously, this is because of some tensions that exist within these two data sets. So now let's move on to, let's say, a more solid model, which is going to be a coupled quintessence model. So first of all, a quintessence model, okay, so is basically described by a scalar field, which will be representing the dark energy part. Okay, these are quite interesting models. So for instance, if you study them via dynamical analysis, you will end up with the tracking nature as well as the scaling properties of such models. In this case, we'll be considering the dark sector, which will not be basically independent from the dark sector constituent. So that is, the components within the dark sector, they are now going to be linked to one another. Okay, so in the general, let's say, scenario, we assume that there's no interaction between the dark sector constituents. In this model, I will be considering that there is an explicit interaction between the two components. And in this case, we basically evade the very tight constraints that we were basically restricted in the standard model regime. Okay, in this scenario, since we are dealing with the dark sector only, those constraints do not apply, and therefore we can consider this interplay between dark matter and dark energy. So let's move on to the theoretical framework, that is the action formalism that I will be considering. As I said, it's going to be a coupled quintessence model. So the first term, okay, so the Ricci scalar part is just the standard GR term as well, okay? But then for the matter sector, I will be considering a scalar field, okay, which will be directly coupled with the dark matter regime as well. So in this case, you've got the standard kinetic term, okay, and a potential, V of phi, and then you've got the standard model particles, which are living on the G mu nu metric, okay? So they're basically coupled with the standard metric. However, then I'm going to consider the dark matter sector to be coupled to another metric, which is going to be related with the metric G mu nu. However, the dark matter particles, they are coupled with another metric, G tilde mu nu. Now, this G tilde mu nu is basically related with the, let's say, the gravitational metric G mu nu via a conformal coupling, C of phi, okay? So C of phi G mu nu, and a disformal coupling as well. So this disformal coupling has been mentioned in Tessa's talk as well in the scenario of Horndeski. The reason being is that when we consider disformal couplings, this basically appears in an Einstein formulation of any covariant theory involving the invariant other than R. And in fact, you can show that when we consider these formal transformations, these are well-posed transformations. That is, they preserve Lorentzian signature, they ensure causal behavior, and they are invertible with a non-zero volume element. And one can also show that the Horndeski action is formally invariant under this class of transformations as well. Okay, so that is why they appeared in the Horndeski scenario. So what are exactly these formally coupled scalars in this case? So in this case, we'll be considering scalars which are coupled to matter through derivative terms in the metric, okay? So that is, let's say, what we are going to deal with. And then the link, as I already mentioned, of this formally coupled scalars with other theories is quite significant, okay? So they appear in dark deep brain cosmology, massive gravity, coupled quintessence, as well as Horndeski, okay? And there are a number of cosmological signatures. So that is why they are quite interesting to study, because we can actually study their cosmological signatures at the background level as well as at the perturbative level. So from the, let's say, theoretical side of this formal couplings, we can think about this formally coupled dark sector from the point of view of brains. So we can consider a moving brain, okay? And essentially we can identify the scalar field to be the radial coordinate, and that is why we normally refer to the scalar field in this case as the dBi radion, okay? And if the brane or the dark brane is not intersecting with the standard model stack of branes, then that means that there is no link, okay, between the two sectors, i.e. this formal coupling is only acting within the dark sector and not within the baryonic sector as well. So with this framework, what we're saying is that dark matter stems from the oscillations of the open strings in the directions along the brane, okay, because this is a moving brane. Phi, as we said, is the radial direction, so it's the dBi radion, and gravity emerges naturally from the oscillations of closed string in the bulk space-time. Okay, so there is this kind of unification framework. Okay, so now let's move on to the field equations so that we study the cosmological signatures. So when we consider the field equations, okay, we would be expecting a non-conservation of the energy momentum tensor of the scalar field, T mu nu phi, and in fact the Klein-Gordon equation, we end up with a coupling term Q, okay, and this Q is dependent on the coupling functions. In this case, they are the conformal coupling function C and the disformal coupling function D, okay. They are explicit, so this coupling function is explicitly dependent on these coupling functions C and D, as well as the energy momentum tensor of dark matter. So again, since there is a non-conservation of T mu nu phi, then there is a non-conservation of T mu nu dark matter. Okay, so the energy momentum tensor of dark matter is also not conserved in this case, and therefore the right-hand side is non-zero, and again is proportional to the Q term. However, since standard model particles are uncoupled, therefore we expect that they will follow the standard conservation equation, and indeed that is what we get. Okay. Now let's consider the spatially flat FLRW line element. Okay. In this case, I will be working in conformal time tau. Okay, with scale factor A of tau, from which we can derive the standard Friedmann equations. So again, h squared is proportional to the sum of the energy densities, and the conformal time derivative of the Hubble parameter is again the standard kind of equation, okay, where we have the energy densities as well as the pressure appearing for each fluid, including the scalar field. Okay, and as expected as well, the standard model sector, over here we are considering the radiation sector as well as the baryonic sector as well, they will follow the standard evolution equations. However, since there is a coupling within the dark sector, then we will end up with a modified Klein-Gordon equation. That is, the right-hand side of the Klein-Gordon equation is proportional to Q, as well as the dark matter conservation equation. We've got again a non-zero right-hand side, which is again proportional to Q, and the derivative of the scalar field phi. In the case of FLRW, the coupling function Q simplifies considerably. In fact, it simplifies to this term. Again, it's dependent on the conformal coupling as well as the disformal coupling, as well as their derivatives with respect to the scalar field. In the case of a pure conformal case, that is when you switch off the disformal coupling, you will end up with a much more simplified version of Q, from which case, if I consider the effective coupling function, that is Q on rho C, I will just end up with log of C comma phi, okay? So if I consider an exponential function for the conformal coupling, I would expect Q on rho C to be a constant. And indeed, this is what I get. So in the top left figure, I'm basically illustrating the effective coupling Q on rho C, for which in the uncoupled case, which is the green solid line, that is simply zero. In the case of an exponential conformal coupling, because of the previously derived equation, we expect that over there that will be constant in time, and in fact that is what we get in the conformal case. However, when I consider a disformal coupling, I will get a late time coupling, okay? In fact, the coupling switches on at late times only, and switches off at early times. And a similar scenario is also illustrated in the case of a mixed coupling. Okay, that is when I have a conformal coupling as well as a disformal coupling. In this plot, so on the bottom plot, I'm illustrating again the deviation of the energy density of cold dark matter from the standard evolution of a to the minus 3. And again, as we might expect, we are getting a deviation, okay, from the standard a to the minus 3 evolution as expected via decoupling. Similar illustrations are here denoted with respect to the effective equation of state of cold dark matter, which is basically the red line, for instance, and also the deceleration parameter, the dotted line. Okay, but if we focus on the red line, which is the effective equation of state, due to the coupling, there is a deviation from a zero equation of state for cold dark matter due to the coupling within the dark sector. So over here we have a conformal coupled case, and on the right we are considering a disformally coupled case where you can see that there is quite significant deviation from a null equation of state. Okay, a similar illustration is shown in the bottom figure where we are considering supernovae data and the residual difference between the absolute magnitudes. Okay, so let's move on to the perturbative side of coupled quintessence model. So if we consider the Newtonian gauge line element with standard potentials psi and phi, and we just focus on the perturbed continuity as well as Euler equations of coupled dark matter, we'll end up with new terms on the right-hand side of the equation. Okay, these are basically either proportional to the background evolution of the coupling function Q, or else to the linearly perturbed coupling function delta Q. As we might expect, similar terms will appear also in the modified perturbed scalar field equation, okay, which again we end up with a term proportional to the linearly perturbed delta Q as well as the background evolution of Q. All right, where in this case the delta Q equation is written down here just for reference, but I will suggest that you refer to the to this reference if you would like further information on all the terms. I should remark that these bi tilde terms, those are dependent on background evolution quantities only. So let's now consider the matter growth rate function. Now, by matter growth rate function, which has already been mentioned in the previous talk, I'm referring to the total matter density contrast, okay, that is delta M, where it is including the baryonic sector as well as cold dark matter sector, okay, so all in one quantity. And if I consider the growth history, okay, along the x-axis, denoted by Fm sigma 8 quantity, and along the y-axis, I'm considering the Hubble expansion H on H naught, you can see that I can distinguish between uncoupled and coupled models via this plot, right? So you can see that, for instance, coupled models are normally characterized by an enhanced growth, especially illustrated by this turnaround, okay, where you can see that in the case of this formally coupled models, the turnaround happens at roughly the same redshift, okay. However, there is a much more enhanced growth with respect to the uncoupled model, that is the solid line, as well as the conformally coupled model, right? So let's try to understand why this is happening. So essentially, if we consider the small scale approximation, okay, of the evolution of the dark matter density contrast, we will end up with an effective gravitational constant, which I should remark, gravitational constant is only acting on the dark matter particles, okay, it's not acting on baryonic matter. And as you can see, there is always an enhancement in the effective gravitational constant because it's 1 plus an additional term, which is always positive definite, okay, because it is a squared term. And therefore, that is why I would be expecting an enhanced growth. because of the fact that there is an enhanced effective gravitational constant, which would lead to an enhanced clustering within the dark matter regime. Okay, so that will lead to a significantly enhanced growth within the large scale structure as well. So in fact, this is the plot for the effective gravitational constant as a function of the scale factor. Again, there is a late time enhancement in the case of this formal coupling and a constant enhancement in the case of conformally coupled model. This is a similar now with the density contrast of cold dark matter. So as you can see, again, if we consider a normalization at redshift 2, you will still see that for this formally coupled models, the enhanced growth is more pronounced with respect to the growth rate of uncoupled and conformally coupled models. We can consider the growth rate function Fm as a function of wave number k in h inverse megaparsecs, as well as redshift. So over here I'm considering 4 different redshifts between 0.5 and 0.56, and you can see that at small scales, okay, the matter growth rate function is much more enhanced with respect to the large scale theoretical prediction. And this is a characteristic of conform coupled models, okay? And then at intermediate scales, you will end up with this, let's say, pronounced bump, okay, which leads to the enhanced growth at smaller scales. As you can see, this is also true for redshifts between 0 and 1, and actually higher redshifts as well. If we consider this formally coupled models, what will happen is that on top of the enhanced growth on the small scales with respect to the large scales, there are also damped oscillations at intermediate scales, okay? So we'll end up with damped oscillations, okay, just after the first bump until we reach a plateau at smaller scales. Now, unfortunately, these oscillations are too small to be currently detected by current observational probes, and moreover, these damped oscillations do not appear in the matter column. So these will be quite challenging to be, let's say, a discriminant factor, okay, that is by which we can distinguish between this formally coupled from conformally coupled models, okay? But theoretically, these are predicted. However, observationally, these might be quite challenging. Now, since we had, in the case of this formally coupled models, first of all, there is a scale dependence. So you can see that the bump here is shifting as a function of k, but we also know that at higher, okay, this formal coupling dilutes, and in fact, we can see that the oscillations, okay, are damping quite significantly at higher redshifts, and indeed, at around redshift 1.5 or so, you will end up with no oscillations at all. A similar result is also expected. In fact, that is what we get for a mixed coupling case, okay, due to this formal coupling. So we get, again, the damped oscillations and an enhanced growth on small scales with respect to large scales. Similar plots for the evolution of the matter growth rate function as a function of redshift and wave number as well. Okay, so another probe is the integrated Sachs-Wolf effect. So first of all, this effect is quite minute in the TT spectrum on its own. So if we consider the TT spectrum and then the ISW signal, basically this signal is around about 10 times less than the TT spectrum. Moreover, there is cosmic variance at those multiples, and therefore it is quite challenging to use those multiples in order to confront cosmological models with that data. You can enhance that signal by combining the CMB spectrum with the with large-scale structure probes, essentially. So basically, this is what I will be considering now. So I'll be cross-correlating the TT spectrum with the over density spectrum. Okay, in this case, I'm going to consider galaxy over density spectrum. So the tracer is going to be galaxies. And over here, this is the mathematical definition of the CLTG, cross-correlated angular power spectrum, where you can see that we have the weight functions coming from the temperature of the CMB, as well as the over density delta LG. And also in the equation, we have the primordial curvature power spectrum, which appears also in the equation. In this case, I will be considering the WISE galaxy over density map. There's now publicly available more updated map, which is the UNWISE as well. And I will be using the Planck 2018 CMB temperature map, combining the two together to get these data points. Okay, so we've got a cross-correlated power spectrum as a function of multipoles, which in this case, they are binned data points. As you can see, current data is not that, let's say, is not that strong in order to distinguish between one model and another, and also in order to confront models with a statistical approach. However, we can get an indication on, let's say, the true models, or at least the profile of the theoretically predicted signal. It will follow at least the current bounds that we have at the moment, which hopefully will be enhanced in the future. So you can see that the lambda CDM prediction fits very well the current data points, okay, and the profile is very well consistent with these data points. If we consider a conformally coupled model, which is the blue solid line over here, you can see that there is an enhanced signal with respect to the lambda CDM theoretical prediction. If we consider the disformal coupling within the dark sector, you can see that there is a dilution effect, okay? So there is a suppression and not an enhancement. So this can be, let's say, another characteristic. In this case, it's first of all a theoretical characteristic, the case that with better data, we would be able to distinguish one model from another. Although we might expect some degeneracy because you can mimic one coupling with another if you consider different coupling functions as well. But let's see with upcoming data as well. Okay, so what is the current status of these coupled models? So if we consider the conformally coupled models, that is on the left-hand side, in this case, I'm considering an exponential function, okay? So exponential 2 alpha kappa phi, where alpha is basically the coupling strength parameter. So you can see that if I just consider the Planck data, okay, so here I'm considering the TTEE as well as the lensing data. Over here, you can see that with just the Planck data, the coupling strength parameter in the case of the conformal coupling is very consistent with null coupling, okay? However, when I consider a prior on the Hubble constant, which is not consistent with current CMB data, and over here I'm referring to the Rees prior essentially, okay, which is at roughly 3.5 sigma higher than the inferred Planck H naught value. What you'll end up with is that you'll end up with a bump, which is roughly around about 2 sigma statistically significant deviation of alpha from null coupling, okay? So it might be the case that if this tension within, so between the Hubble constant values, let's say, is more pronounced in the future, then this could lead to at least give way to these kind of models, okay? But at this point in time, it is not that much statistically significant. If we then introduce the cluster abundance data sets, that basically these are probing the F sigma 8 regime, okay, so the growth history of these models, then again, the obtained constraints are in a very good agreement with the Planck inferred constraints as well. So over here, we can see that conformally coupled models are tightly constrained with current data. And even with only CMB data, you can place very tight constraints on this model. If we consider this formal models, and in this case, I'm considering a very simplified model that is with a constant, this formal coupling, dm, you can see that with this gray region over here, you can see that if I just consider the Planck data set, okay, I'm not able to place a tight constraint, or else not even just a constraint on this formal coupling. Reason being is that since this is on the theoretical prediction on the CLs of this kind of model. Okay, so basically the deviation is insignificant with respect to the CDM prediction, i.e. You cannot basically put any constraint on this formal coupling. However, since these models are characterized with an enhanced growth rate, okay, therefore I would be able to impose stronger constraints with the use of cluster abundance datasets. And in fact, this is what I'm illustrating with the blue and red regions, in which I'm using cluster abundance datasets. Again, they are basically making use of the growth rate data point, okay? And since a large, in this case, a large disformal coupling leads to an enhanced growth rate, therefore there is, let's say, an upper bound on the disformal coupling. But again, we are still, so current data sets are still not able to tightly constrain such a coupling, i.e. it is still allowed with the current data sets. In the case of a mixed scenario, what will happen is that, so for example, over here, what I'm actually comparing is the blue region. Okay, so the blue contour is representing the conformally coupled case, okay, which is, as you can see, it's in very good agreement with a null coupling, okay. However, when I switch on this formal coupling as well with the conformal coupling, the constraints will become looser, okay, and especially the gray region is the generic case of a mixed case, that is, you have this formal coupling as well as a conformal coupling. So again, a much larger coupling is allowed in this case. But again, there are more model parameters, and the current data sets are not that constraining these kind of models very well.
Sorry.
So over here,
Jürgen, you have 3 minutes. That's fine.
Yeah, thank you.
Yes. Thank you.
So basically over here, this is an illustration of the enhanced growth rate. So you can see it over here. So in this bottom plot, you can see from the colored dots, so the red points, they are basically signifying a very high sigma 8 value, okay? And that is why the cluster abundance data set is basically forbidding this that region. That is why we are imposing actually this upper bound on this formal coupling, okay? When we use the cluster abundance data set. So again, referring to GW 170817, which has been mentioned previously as well. As I said, when we consider the Rees prior, okay, we end up with a non-null, let's say, preference of the conformal coupling within the dark sector. And due to the fact that the gravitational wave current constraint on H0 is very loose at the moment, again, obviously this implies that it's consistent with the Planck value of H0, i.e. there will be no change between the contours, okay, that we obtain by imposing the gravitational wave H0 value along with the Planck constraint, okay, so you can see from the red and green regions. However, at around about 2 sigma statistical significance, you'll end up with a non-null value for the coupling strength parameter. Okay, so these are the conclusions. Take-home message is that essentially at this point in time, we still need to work on these kind of models. That is, by trying to actually impose tighter constraints on these models. We can also explore other avenues. That is, for example, we can consider what are known as tidal tails of disrupting satellite galaxies, which have already been used in the case of coupled dark energy scenarios. We can also look at the nonlinear evolution, and another probe, again, from large-scale structure is the CMB lensing tomography, which is particularly at low redshifts, i.e. that's going to be quite a good probe for this formally coupled models. Okay, and that's basically it from my side. Thank you.
Hey, thank you very much, Jürgen, for the nice talk. If there are any questions, please, you can raise your hands or write it in the chat and I will read it for you. Okay, yes, Cesar, can you go ahead?
Yes, thank you. Thank you, Jürgen, for a very nice talk. Foundational question for you. So when you said gravity, that there is a violation of the equivalence principle in the dark sector, what you mean is that gravity is a non-universal force, right? And then you write up the Lagrangian for the dark sector with this twiddle G metric and all these non-conservation laws for the energy momentum. But why don't you compute, or is there a reason why you don't use that metric to compute these conservation laws as opposed to the space-time metric?
Okay, so you mean using G tilde instead
Yes.
of G mu, right? Right. So reason being is that you will end up with a Horndeski-like theory, and as you know, for Horndeski-like theory, the equations become a bit cumbersome, and in that case, therefore, the evolution equations, let's say, they are much more challenging to numerically solve and actually interpret in Boltzmann solver codes as well. So that's the main reason.
Yeah, but well, I mean, it seems that it would be more natural to do that, right? Rather than say this is a non-conservation law. I mean, you need to have a source for that dark energy sector otherwise.
Yeah. So basically, what will happen is that if you consider G tilde mu nu, so if you basically minimize your Lagrangian, so we vary your Lagrangian with respect to G tilde, what will happen is that you will basically modify the gravitational sector. And you will end up with a very similar Horndeski-like theory, in which you are basically changing the left-hand side of your equations instead of the right-hand side. So what will happen is that, in fact, I don't have it here. So instead of, yeah, but you can see it from here essentially. So what will happen is that, as I said, so we will basically modify the gravitational part, that is the G mu nu term. So the capital G mu nu, the Einstein tensor, that will be modified, and that will look very similar to Horndeski. And then you will basically leave the matter sector, let's say, untouched. So that will be very easy to deal with, and that's, as you said, more sort of natural. However, then you have to deal with the modification on the gravitational side of things.
Can I ask a final one now that you're here? Just one last one.
Sorry.
So
Yeah.
from this slide, you consider some null vectors for the space-time metric. What happens with those null vectors in this G tilde metric? Do they become kind of a massive mode or something? Because they're no longer null, right, in tilde G?
I think at this order, we assume that they do not contribute. I think you have to consider higher order.
Right.
In order to get their contribution.
All right. Thank you.
Okay. Thank you.
Okay, thanks. So thank you, Jürgen, again for your nice talk. And okay.